have to.
Absolutely.
This is what
But we can always make it better. Or what happened. Or it's somebody like having you that they want to help.
Yeah.
Yeah. So let's now go to our second speaker, Roussanka. She's going to talk about parametric information via type theory of Acyclic.
So I continue to talk about Moskovakis type theory of algorithms, and I can to give a baby example, but to link the capabilities of the expressiveness of type theory of algorithms, type theory of algorithms with Andreas functions that I consider them as parametric, non-deterministic values can be represented by recursion, by memory variables that can be instantiated, I don't know when, or whether in the runtime but during context. When context brings more information, then those parameters get instantiated. And I really don't know yet whether that can be modeled as values of functions during performance of a program, or just some by the context information, by the state that are encoded by the terms. So one place that's important for language processing, and I believe for the language of mathematics, is still the lexicon, the lexical items and their semantical representations. And one place I'll show now again with simple examples. So I think that the lexicon, the structure of the lexicon is important, and semantics to be represented by parametric semantic parameters. And then the lexicon can be classified with respect to the part of speech nouns. There can be relational nouns, father of, successor of, these are relational nouns, or which means at least two arguments, or just single argument nouns, just like the verbs. Verbs, they can be transitive or intransitive, and they can have multiple arguments or single arguments. For the intransitive, verbal phrases which designate predicates, their expressions designating predicates over entities and mathematical objects, they are also parameters and can be instantiated depending on the specific lexical items. So this is one huge place, the lexicon, where I think the parametric information is important. Another place is that we have been talking today for the scope under specification. The order of the scopes creates ambiguity. There, the parameters, if you want, I can go back for the same example that I didn't show actually in details for the quantifiers. And today, actually here, I'll show the verbal phrases themselves. They can be parameters. This is when we have a verb phrase ellipsis, which means a verbal phrase can designate one or another object depending on what the head verb takes, and then it can be also antecedent dependent. And now I will, and there is a very nice criteria for the verbal phrases there for what they can pick up as arguments. But here I'll remind, most people already have seen this slide quite many times, but I'll repeat it again, just to describe what type theory of algorithms is, especially Moskovakis type theory of recursion of algorithms. And then I'll show again only the syntax. And the semantics is with examples. So the important thing is that we have two layers of semantics. in the formal language. So right now I talk about LR and AR. One of them is simply type theory of acyclic recursion, acyclic algorithms that are ending after finite number of steps. And the other one is LR, is full recursion, where we may have cycling algorithms. Then each term in this formal language has the notation. The notation of function follows the syntactic structure of the terms. And then the important thing is that here the formal language itself, its machinery, defines algorithmic semantics, which means that there is a formal way to specify how the denotation of one or another term get computed. And there, it's one important thing for all of us. So Skouakis introduced the recursion operator at the formal level. It's a term, official formal term that designates the recursor operator. And this is the key feature of the syntax semantics interface between recursion theory at the level of semantics. Recursion theory is a mathematical structure of recursively defined functions, and a formal language for that recursion theory. And then here, if it gets very nice application for the semantics, algorithmic semantics of the natural language, let's say English. So here, natural language gets its semantics just like programming language. Programming languages, they have the notational semantics and algorithmic semantics. And here, with this formal system, we can interpret, can use this type theory to annotate terms, expressions translated into this formal language with terms that represent the semantics of those expressions. So now, how does this happen? The notational semantics, as I told you, follows the structure of the terms. The algorithmic semantics is determined by canonical forms of the terms. Each term, every term in this language, can be decomposed into canonical form. And this canonical form represents the algorithm, which means the program that computes the denotation of that term. Of course, that is valid only for the algorithmically meaningful terms, and not all terms are algorithmically meaningful. I hope I put the slide to show you which terms do not have algorithms. But the good thing here is that every term, it doesn't matter whether it's algorithmically meaningful or not, it can be decomposed after finite number of steps into its canonical form. And if the term is algorithmically meaningful, then the canonical form tells us what are the steps to compute the denotation of that term. So the good thing here is that this reduction, reducing every term into its canonical form, is effective. Whatever term we grab, after finite number of steps, we get its to the program for computing its denotation. So I have been trying to improve the efficiency there, to make the algorithms more efficient, because in the original reduction calculus, the complexity, those algorithms quickly explode exponentially. So informally, intuitively, the reduction calculus decomposes a recursive program into its iterative alternative, which means that factor reduction already is not a dictator there. It is very important, and it's valid for the notational semantics. And it's very important in deciding whether two terms designate the same algorithm, which means that whether two terms are algorithmically equivalent. But it applies only at a very, very basic step, only to terms that cannot be reduced, only to terms that are explicit without a recursor operator in them and irreducible. Otherwise, beta reduction may start with a recursive program, and if we apply beta reduction, we may get back the recursive program, which is not the purpose here. So the type system is the Gaussian type system. Symbol S, the blue one, it designates this is a type for a state, for context information. In the provers, this can be interpreted as a state of all the theorems that are assumed. But otherwise, it's just lambda calculi. E is for entities. P is Boolean. The new thing here, the important thing here, that we distinguish between truth values that are state dependent and truth values that are not state dependent, which means that that's important to the natural language. The interpretation of a sentence depends on the context, which means on a state, and the state can represent the memory state of a computing system, or a human agent, or a robot, artificial system, or, as I told you, the preliminary assumptions in proof systems. And then we have the functional encoding. Tau is for functional, for Curry encoding of the and place relations. So then we have type vocabulary constants in each type. And the other thing that's very important is the variables are divided into two kinds for each type. So that is a very natural choice, which at least didn't occur to me, but it has been all the time under my hands and under the hands of every one of us. So the variables, we use them in mixed way. When one way in lambda calculus for functions, we use them to denote objects in the semantic space, in the semantic domain, and then we can abstract over those variables by lambda abstraction, or to quantify over them by the logic quantifiers. And there is another kind of variables, those are the memory variables, which means that memory variables, they designate memory slots in a computing system. So this is very important to distinguish between those two kinds of variables, so we should not mix them up. So which means that again, lambda abstraction and quantification over recursion over memory variables is not directly allowed, but there is a trick one to abstract over them too. So then comes the syntax, and the syntax you see quite quickly. Hey, it's lambda calculi. Any lambda calculi has the variables are terms and the application term, the lambda abstract. The important thing is for the algorithms is 3B. So actually 3B makes de facto lambda calculi into a language for the recursive programs that can be translated, that can be reduced to iterative programs. And then 3C, 3D, and 3C and D, I have included there the logical operators in this tricky way as constants. Of course, we keep them as logic constants, but here one can use them as any constants because there is a special reduction rule for the constants, and in this way I get it more efficient to express the reduction rules. Pure quantifiers, they should be introduced on their own as logic, pure logic quantifiers, not to mess up with the general quantifiers. So I have included an example with interpreting the definite descriptor either as a pure quantifier in a Russellian way or it's a generalized quantifier. And the other important thing is 3F. 3F is introducing restrictors. Each term can be restricted. The denotation of a term 80 can be restricted with respect to by some propositional terms. Some people ask me why don't you use implication there? So implication is still proposition, but an implication formula, if A then B, it has propositional force. While this, the restrictor term, it has referential force. In recursion theory and in programming, this is it's a generalization of the mu operator, which means that the least in the world of the numbers and the functions in arithmetics, it corresponds to the smallest number k such that C1 to Cm are true. And then it introduces a partial referential force. So I think this is important for the natural language, even for the quantifiers. So 3G and 3H, I don't have at all time to talk about them, but these are the intentional. This is intentional versus extensional interpretation of expressions, and these are important for natural language and including the language of mathematics, because the mathematicians, we write statements, we write theorems, and the statement of the theorem has, for example, noun phrases or verb phrases, and the mathematician refers to some mathematical objects directly through in the scope of the statement of the theorem or as if external descriptor of what the theorem states. So theorems can be scope ambiguous in that way. And to scope means that we translate the theorem statement or lemma, translate it into a term in this theory, and then certain sub-expressions, certain sub-terms, they have to be taken out of the scope of the theorem so that the mathematician refers externally to certain mathematical objects. So this is important also in belief, in logic that represent beliefs, knowledge, but it's important in theorems and in proofs of theorems. So this is actually the syntax, and talking about the terms, actually I have been talking about the denotations of those terms. And now how we get from these terms into their canonical forms. I'll tell you in a moment about the canonical forms. As I mentioned, there is a reduction calculus. One may say, okay, we translate natural language of mathematics into Montegovian terms, and the Montegovian terms, they represent the recursive programs. So whatever a verbal phrase designates some predicate, and then predicate is applied to the subject noun phrase of a sentence. So in Montague is very good, Montague intentional logic, very good, provides terms, recursive terms for that. But then what we do, for example, a Montague term will translate the verb phrase, and that term will apply to the translation of the subject noun phrase, and then we start better, because it's going to be an intentional logic Montague. So there is a type rising, and then we start beta reduction, and we get to a first order logic term, which is not right. So it's very wrong also beta reduction when we want to represent under specification in natural language. So this is the famous example. John loved his wife, and Peter does too. So who does Peter love? His own wife or John's wife? But John likes himself, and Peter does too. This is more clear. It's more clear, but not enough. Does Peter love himself, Peter, or does he love John? So this is under specification. It's called a verbal phrase ellipsis, and which means that there is a distinction between strict reading and sloppy reading. Peter likes himself, and Peter likes John, or with their wives, story between their wives, but the same syntactical structure with the same semantic under specification exists also in the language of mathematics. So here it is. Did I wrote the sentence or skip? So here, I'm still here in the last stories. Let's go to the mathematical example. So with the previous examples, translations, I tried to get a recursive term, I'll return to it, and then to decompose it. And then we use the parametric parameters, which means memory variables, to designate different specific denotations. But here is the example in natural language. And here, actually, I use the trick, the noun phrase, the number J. And it's a noun phrase, but it uses not only the definite descriptor, it refers to a specific number, but also the number is named J. Probably a mathematician will write the number M is less than its successor, and K is 2. So here we have also another yet ellipsis, and K is 2. So K is also missing. What does it denote? Again, a number, I think, one interpretation. So Muskwakis terms, they give very nice machinery to translate into his type system, in his typed terms, this multiple under specification. And the trick is the parameters. And the parameters here are the memory parameters. So the key thing is that there is no lambda term corresponding to this term. This term is not lambda calculated. Any lambda calculated, it doesn't exist there. Why? So in Muskwakis type system, we have this recursion terms that designate the recursive operator. So there is a theorem which I presented it the other day, and the slides are here. So if such recursion term is such that it doesn't have the recursion operator in it, so the where this is a constant designate that looks like let, but it's not let, it's more powerful. That designates actually recursive computations. If a term doesn't have it, it's called, it's not yet lambda term, but it is a non-recursive term. But if also we forbid recursion variables, so without where, without the operator where, we get explicit term, which means there is no recursion, explicit recursion in them. But if we forbid also memory variables, then it's a lambda term. And there is a criterion if we have in a term, recursion term, if we have at least 2 occurrences of an assignment variable, then there is no algorithmically equivalent lambda term. Of course, it is denotationally equivalent to a recursive term, but not algorithmically. So shall I keep it a little bit on this term, because I really will appreciate some feedback.
What is S1 and S2?
Okay, oh, okay, that's a very good question. So here is a trick with this the number to distinguish between Russellian and Straussonian definite descriptor. So T is the definite descriptor the. And it requires a noun to become really descriptive determiner, a descriptive noun. The number. So C is a parameter, and C can be instantiated with any suitable noun. The number is suitable. But how do we interpret it is with this referential force. So whoever wrote this term designates a specific object, and then where do we get this specific object? The first occurrence of the number J. So we have to apply the noun phrase the number into a state S1, and the object in the state S1 is the number J. So the uniqueness is required only in the state S1.
S1 and S2 are equation.
Yes, these are situations, S1 and S2. Why I'm abstracting vacuously over the state? Because of this state dependency. It's a J state dependent number. The number J depends on the state. And the number P also depends on the state, but we don't want them floating, so we have the same number in all possible. So it's actually the constant function for the number J and the constant function for the number P, but you may prefer other interpretation, don't need to. It really can both changes. The denotation of the number J may change from state to state, which might be more natural way to interpreting the nouns, the descriptors. The descriptors. So here P is really very context dependent. Is it the number or is it something else that is less than its successor? So the number J can start at any place. If we are interpreting the numbers, the natural numbers, it can start at any point of the natural numbers and then have successor. So here the issue is not whether the sentence is true or false, but how do we represent what is the denotation of this term A?
It's ambiguous.
So it took me some time because it's a not so well acknowledged under specification in the language of mathematics. So a mathematician has to be very careful to avoid such sentences. And the same not only with the numbers, I was giving examples with the blocks. The cube J is larger than the cube, larger than the tetrahedron T, then even bigger ambiguity. The sizes, they are context dependent. So the cube J, the large cube J is larger than the tetrahedron P. So then the property large and larger, it is state dependent with respect to the volume. So one has to define threshold for large and small cubes. You gave an example, what was it, with elephants and elephants. It's not the same to have a large elephant and large fly. I think there were examples with mice, large mice. So this is my motivation. This example shows clearly that it's not only quantifiers. It's also verbal phrases. So here again, we have this H1 and H2 are completely free recursion variables. They can be linked in different ways for this underspecified lambda. Well, it's not lambda calculus. It's
S1 and S2 are also free.
Yes. Yes, they're free too. Actually, I believe that it's important to use the states and the situations to designate them with free variables, because what exactly is the context? It's kind of an open collection of information. So situation theory is very good in that states are not so sophisticated, but states, they can be used also to represent a lot. The problem with the state in this type system is that it's very difficult to encode inflection, information that comes from inflection of the lexical items. It's okay. So this is what I wanted to tell you today. So I'm done. But here I just present different options, how to interpret different instantiations. So there are several different instantiations. Here is my motivation about parametric algorithms. So the big question here is, just like what Adrian represented in functional programming languages, what do we do with functions that have multiple values? So here I use memory variables as parameters, as if they're uninterpreted, and they're interpreted. We get them in specific contexts, but typically the programming languages, they are not happy with free variables. They have to be at least, at the minimum, declared as local parameters. And I think this theory is very good in doing this. So even the constant here, in this set of slides, I didn't present the reduction rules, but the reduction rules treat, in this theory, they treat constants as algorithms. And that's quite natural. Even for constants that designate natural numbers depending on the number system, whether it's base 10 or base something else, 8 or 12. But also, Plakis gives the example, for example, of a constant that is very serious algorithm, the number pi, 3.14. So in the lesson, each lesson in programming languages starts tells the students, declare your constants at the beginning of your program, and then don't scatter this constant p through your program, because then the program is going to stop at each occurrence of the constant pi, p, whatever you pronounce it, and to recalculate the value again and again. So declare all constants because they have algorithm meanings. Declare them at the beginning of the program, and then use the values rather than the constants themselves, which is exactly an argument not to apply beta reduction if we want the program steps for computing the portions of the programs. Well, natural language of mathematics is quite ambiguous, actually. We just need to be more careful, because that language, depending on its own subject area, allows us to be more careful and to write more carefully syntactically well-formed expressions, and then to follow. But we have ambiguity. It has to deal somehow with the ambiguity. It's not always ambiguous, as we see. It's under specification. Not every book is given its value and value pattern. So here I don't know whether multi-valued functions getting whatever values they collect during runtime, or suppressing any interpretation. I would think now and then I think that the evaluation they have to be suppressed, and then actually we'll have what we are talking here about the theorem, the provers. For example, natural deduction, we have been talking about natural deduction. Natural deduction rules, usually we express them and we tell this is in a meta language. We use meta variables to write down the natural deduction rules. But with this theory, we have already the possibility to express the rules of natural deduction at the object level. We don't use meta variables, we use memory variables, which means that the prover can have more efficient ways to save things that are already theorems and lemmas that are already proved. So it will save in memory proved statements and reuse them, and it's what mathematicians are good. The proof objects, they should use a lot of this, and they use that, so that improves huge proof trees. So the branches, they can be separated and saved and reused. That lemmas are about that, right? And then the lemmas, they are expressed with parameters. We usually call them with meta variables, but they are actually memory locations where we save things that are proved, and then we instantiate them. Instead of C instantiated with Q, it will be, or C with number, then it will be instantiated with a small lemma or bigger lemma. And the C, the number, it will be instantiated with one or another number. So that's what I wanted to tell you. So here, a conjunction and disjunction, they can be interpreted in the standard Tarskian way. But here, as I told you, and here I wrote them as with infix notation. But here one can save reduction rules by using the conjunction, disjunction as a legal constant, and then this constant will be applied. Here one has the choice whether the conjunction applies to the left subformula or to the right formula first. In all these terms that I have written, I have followed the natural language structure. A verb, which means conjunction, and it's a conjunction operator, probably apply to the right subformula, to P2 at first, and then to P1. So we get ordered junctions and disjunctions. The verb phrases, the head verb applies at first with to the noun. If it's with noun phrases, it applies at first to the object, the complement of the verb, of the head verb, and then to the subject. So that will follow English structure. But in GF, there is no right, there is no order. Some languages are order independent, so that will be syntax. And I think that conjunction, disjunction, that will be also concrete syntax. So the quantifiers also, we can put them. The quantifiers exist for all. Usually we write them as prefixes. We can change that. Generalized when we treat them as generalized quantifiers, we follow the logical structure. Exists X such that A, but in fact there is no one can put it at the end. So this is abstract. A correspondence relation between abstract and concrete syntax. So this is with this example, and I'm eager to hear questions. Which means that probably you hate me because I'm opening a lot of provers, but it's not a lot. It will save a lot of time, make the prover proofers, especially the automatic, more efficient by having patterns of proof rules rather than meta language natural deduction, which is usually the case. So Arne, I will appreciate very much feedback from you, but from Krasimir too, because there is a distinction between abstract and concrete syntax. So here I told that the logical operators, the order that what I think it's, or the order of the conjuncts there, P1 and P2, this is concrete syntax. Otherwise, the conjunct, it can be prefix or in Polish notation at the end. The same with the quantifiers, the logic, pure logic quantifiers.
Any more comments or questions? Yeah.
Yes.
So in this example, H1 and H2 determine how J and P are interpreted.
P1 and P2. I couldn't understand what you were asking.
So H1 and H2 are used to interpret how
Yes. How? Yes.
how
Exactly.
J and
Yeah.
P
Yes.
are.
Yes.
And
H1 can be the successor of W is the successor operator, which means L large designates the relation larger than, and then H1 can be instantiated either with the C or with the with J, either with J or with P, because P can be less than the successor of the number J, or the other way around. P can be less than its own successor. So here we have at least two ways to link H1 and H2. I think I go to the love stories with John and because there I explicit here. The strict reading is John loves his wife because the structure is absolutely the same. So here John loves his wife. Then we get this H1 instantiated with the constant J, or the other way around. Peter does too. So Peter loves John's wife, and then H2 gets linked to whatever H1 designates. Here we have one more strict reading than the usual linguistic. We have extra interpretations. That's also the link according to.
So I think was there someone else?
Ask me, yes.
So I think if you take us back to these sentences 4A and 4B, because John loves
Yes,
himself, versus John loves his wife, and I think they have essentially the same structure. But it's not so clear in English. But I think they are both reflexive, or could be reflexive.
Yes, that's true.
And
His own. One needs to put
and
this
then,
additional own.
the two is referring to the verb phrase. Love his wife, or love one's wife, let's put it that way.
Then there is another yet somebody's else. They pick
Yes.
they
But,
pick interpretation.
And so I think these two are very similar.
Yes, that's true.
And there is the ambiguity of what is the verb phrase that corresponds to two. And you can't escape. There are these two.
Yeah, even three. Only the reflexes is relatively restricted because himself has to co-refer.
Yes.
It has to co-refer the preceding syntactic argument, and this is a good place to make a connection between semantic argument and syntactic argument. But the structure, you are right, there is absolutely the same.
But then you would say that in 4A for A, there are 3 readings actually, which is where the first he is comes from outside.
Yes. That's the purpose.
It could even be Peter.
Yes. So it's
Yeah.
very underspecified. And in this way, with these terms, we catch more one structure, we catch more semantics.
And the question is if you want to allow this kind of tool in mathematical language. Or not, maybe not if we want to allow, but whether it's ever occurs.
We have to be careful. That's the lesson here. But otherwise, we have formal way to represent it formally. It's a term.
One of the several millions of mathematical articles. It should appear at least in one place.
It took me a little bit time to figure out what example. It was more difficult to think about geometric objects because when one needs to define what means successor cube or a neighbor or next, one needs to order them. But it applies to any order, not only to successor. Any order, partial order, is very vulnerable to such underspecification. And the question is, of course, how in functional programming languages, how we allow this when we interpret those values when they get, or my own favorite ways, we don't interpret them, we keep them as parameters because they are semantic. The same with the quantifiers. So Montague, he disambiguated, he translated natural language into special language of the tree structures, which means that he disambiguated natural language, extra syntactical structures. But do we generate all possible tree structures? Or I think we better keep them as parameters. It's semantical level. Syntax, I think abstract and concrete syntax is a good thing. And then, and I think that abstract syntax here has more direct relation to these 3 possible ways.
So I can see in first example for A that there are 2 abstract syntaxes. And for B that there is just 1.
Yes, exactly. That's what I had in B.
But for A has 3 semantic trees. For B has 2.
Yes.
That's at least
But we have to keep those ambiguous, those alternative denotations.
When I think about your slide, it's the assignments. It's double count equal.
Here.
Yes, so this thing, I see it either as a parse chart or the parse storage, or in a non-deterministic functional language. There are choice variables, and each variable can be assigned in a number of possible ways. So this is how I implement it internally in GF even, but it's not part of any calculus that is visible to the user. For me, this is just hidden implementation thing.
That's what I did in my thesis. I did it as semantical storage. Not syntactic, because Montague's you can still stack up different trees in a storage without. That is what I actually the semantic storage. You don't keep the tree structures. Alternatives, you disconnect them,
yes.
and you keep in the storage the disconnect.
So this is the same thing.
The same, yes.
Okay.
One disconnects, and if one focuses more carefully on the quantifiers, you see they have common syntactical structure.
And
From
something
you.
understanding that's what they
Yes, exactly the same. Yes. The only thing that didn't occur to me when I was writing my thesis is about get terms for recursion and to convert the recursive programs into iterative programs because compilers are doing this work. So it has been all the time available to us through the compilers and people in programming, in designing, in programming language designs. They have been using this formal apparatus all the way along, so the issue there, according to me, was this mixing up two kinds of variables. Variables that are memory location and variables that are for lambda abstracts and for quantifiers.
Yeah, I call them meta variables and lambda variables.
Yes, one can call them whatever.
When you want non-determinism, then the meta variables can have many possible values.
Yes, exactly.
Okay.
That's it. Here one goes, pushes everything into the at the object level of the formal language. So it's a very, very ingenious thing that Socrates gave us. There is one thing that really surprised me pleasantly when I list those restricted variables. So in situation theory, I just grabbed whatever Barwais and Etchemendy philosophically laid out, including the admissibility theorem by Barwais. And then I grabbed those ideas, philosophical ideas, and I designed a tremendous recursion system, but at the semantical level. And then there, the semantical level, what I was doing with these parameters or meta variables, I imagined them as semantic objects, and they had to be restricted. You cannot put in a memory slot whatever. It depends on the data structure and on the, because I was thinking about natural language. So you have to think what you put in a semantic parameter. You put there a noun, and the noun is a property of entities, and so forth and so forth. But I thought about them as memory locations, and I messed them up again as everybody else is with quantifiers. There I have two lambda abstracts. One of them is lambda abstracts over something that look like first order logic propositions, and then one gets complex relations. And the other one that corresponds very directly to Per-Martin-Löf dependent types. I used lambda, semantic lambda, to abstract over propositions, and that was in my mind. It continues to be the type, and it has direct translation to Per-Martin-Löf types as propositions. But it was semantical. I didn't occur to call it dependent types. For me, it was recursion, you know. And then with this language, I wrote those restrictor terms, and I have also reduction rules for the restrictor terms. And when I reduce them to canonical forms, and whoop, those restricted terms, they correspond exactly one-to-one with those restricted semantic objects in situation theory. So that was a pleasant, I didn't intend it, it's just the way it is. So that gave me kind of a feedback that I am in the right track, but I may have a lot of errors, so you fix them. So that's, I hope I didn't take too much time, but I have taken, because now is the talk by Larimos.
And now it's
Coffee break, okay.
So there are no more questions. Let's thank
Don't stop me, I can talk probably for 1 month here.
Thank you for the fun.
Next we'll have instantiation also. It's a parameter with different speakers, but I think we get constant. It's for people who work